this from a particular perspective. I was privileged enough to be on the National Academy of Science Committee, where we wrote the precision medicine report. And I don't want to go long on it, about it, although now it really seems like ancient history, because I was with President Obama when he launched the Precision Medicine Initiative back a year and well, whenever January of 2015 was. And what we were thinking about, and among the other authors were people, for example, who had been on the original Human Genome National Academy of Science project. And what we were thinking about was not necessarily only characterizing by genomics, but really that all other data modalities were co-equal. And by looking at a patient from multiple perspectives at the same time, you could get a much more clinically and scientifically useful view. So here's some of the points I'm going to make so that you don't have to stay awake. The points I'm going to make is that most population genetics and clinical medicine is addicted to categorical diagnosis. You have a disease and don't have a disease. We like to think we're probabilistic reasoners, but in the end, when it comes to disease diagnosis, we are categorical. And fake and wrongly taxonomized diseases make social construction of disease likely. And that is both a good thing and a bad thing. Genetics can be genetics first can be a wrong move in taxonomization, and clinical predictive accuracy does not correspond to shared physiological state. And finally, the disease overlaps demonstrates the fundamental problem here. I don't expect you to agree with all the things I say, but I hope at least it'll give you some room for thought. And because I was hearing all these wonderful challenges, I will share with you in my last slide something I put in the last moment, which is a challenge from the New England Journal of Medicine for you to participate in an international challenge to show the trialists that we research parasites can do a good job. But that's at the end. So I'm going to try to formalize a little bit in terms of computer science. We're going to talk about the set of patients across which there's an equivalence relation, and that equivalence relation is going to divide the set into these into this quotient set or quotient space. So, for example, if P is the set of all patients, then the equivalence relation is disease caused by mutation X, then the quotient set is having the mutation or not defines all the diseases. Diseases caused by hyperglycemia and insulin deficiency, that relation defines another quotient space. Diseases manifested by the patient experiencing at least two of the following symptoms: delusions, hallucinations, disorganized speech. If that is your relation, that too will create a quotient set. And by the way, if you think I'm just making these up, I want to point out that last criterion is the DSM-5 criteria for schizophrenia. That's how they make that diagnosis. And to make it even more pointed, that's how in order to be able to bill for it, this is where money hits the road. In order to bill for it, you have to hit those criteria. And by the way, these diagnoses are not just interesting from the point of view of science, but for example, God forbid your child has autism, people will angle all sorts of ways to shove their child, if they have any disabilities, into that diagnosis, because that immediately releases hundreds of thousands of dollars from the school system to give your child the care that you want them to give. But as a parent, you'll do anything to do some ontological squeezing. And that's why there's pitched battles that are engaged in defining what these diagnostic boundaries are. Now, why should we go to a categorical versus probabilistic disease representation? I'm actually not going to hammer on you guys today so much, but why do doctors actually like categorical versus probabilistic disease representation? One of my postdocs, Raj Manrai, did this very nice paper where he just did a copy and paste. He took a question shown here that appeared in the New England Journal of Medicine 30 years ago. And since my host gave me 40 minutes, I might actually look at this. Let's say you, the speaker, what's your name? Jonathan. Let's say Jonathan sits in this room, and we're worried out there because we're beginning to have zombies. And we don't know if he's a zombie or not, because he looks a little bit glassy-eyed. And so, we have a great test for zombiness. This test is unbelievable. If you guys were doing this well, you'd win the competition. 100% sensitive, 95% specific. There's very few audiences I can say that without explaining what I'm talking about. Let's see how far we go with you guys. But it's early days of zombiehood. Only 1 in 1,000 individuals are zombies. We do the test on Jonathan. Uh-oh, it's positive. What's the likelihood that Jonathan is a zombie? Hands up, 90%, 80%, 70%, 60%, 50%. At some point, you are zombies if you don't raise your hand. 40%, 30%, 20%. Thank you for being honest. 10%, 5%, 2%. Pretty good, 1%. All right. Here's the way to think about this. It's 1 in 1,000. Perfectly sensitive test, 1 true positive, you get it. So that's 1 true positive. 5% false positives, 50 out of 1,000 are false positives. So you have 51 positives, 1 true positive, 50 false positives, 51. 1 out of 51 is the chance that Jonathan is a zombie, about 2%. So we asked this question 30 years ago in the New England Journal of Medicine, and we asked it 30 years later. And Raj, my brilliant postdoc, was able to get a paper just by repeating the same question. And what he found is this distribution. So they actually did worse than you. These are Harvard-trained doctors. And half of them were in the 90s, and half of them were right, about 2%. So this is the problem. It's not that doctors are, well, I don't want to argue about doctors, but they are, like the rest of us, not natural Bayesians. But they should be because they're being paid to be diagnosticians. And they'll argue about intuition and so on. I'm glad to have the discussion in the question section. But that's why there's no way we're going to have a probabilistic representation disease. They can't do even basic 2x2 kinds of probability. All right. So, by the way, great title, Medicine's Uncomfortable Relationship with Maths, Calculating Positive Predictive Value. Anyway, I'm not going to focus the study except to make the following point. I was doing a strange study to look at gene expression in the peripheral blood to actually diagnose autism, a brain disease. And I had a bunch of reasons to do that back in the 2005 era because of correlations I was seeing across multiple tissues in the pre-GTEx era. And so the only reason I'm mentioning that is because of that, I was invited to a Harvard Law School meeting because they wanted to talk about my genetic testing. So I didn't think of it as genetic testing. I just thought of it, I was getting an okay-ish AUC in the 70s to 80s on peripheral blood. And so I was like, wow, Harvard Law School, different perspective. I get to talk to these people. And then this guy shows up, and I'm saying, wow, this guy looks familiar. And in fact, I knew I had seen him on television in the previous week. But in fact, I didn't remember who he was until he said the following, the following to me. Oh, you, Dr. Kohane, you're trying to commit genocide on my people. Who's your people? Oh, I have autism. And if your test actually gets commercialized, people will terminate pregnancies, you're going to get rid of my people. As a Jew myself, having some relatives who I went through the Holocaust, it was a bizarre kind of accusation, but he really means it. He was not joking about it. And there's many disease categories where you will actually find these people who say, this is not a disease, this is who we are, this is our identity. But it's important to note this thing that I found on the web when after I got trapped. Let's see if I can read it. I think when Ari Neman talks about autism, this is by a mother, and I talk about autism, we're talking about people with different clusters of autism. I know he doesn't like the word cure. If my daughter could function the way Ari could, I would consider her cured, said Singer. I have to believe my daughter doesn't want to be spending time peeling skin off her arm. Now, so what does this really tell us? It tells us that this disease, autism, is not unitary. But guess what? Her child, if we brought her here, you'd say, this kid, poor kid has a problem. And you look at Ari, you'd just say, his problem is he's an arrogant bastard. And how do we actually, but I want to tell you, most diseases that we look at are of that stripe. And so when I had a lovely postdoc by the name of Finali Doshi join me for 2 years, after her MIT PhD in sort of statistical machine learning and Bayesian dynamics, she did 2 years with me, and then now she's a professor at the School of Engineering and Applied Sciences at Harvard. But she did the following project. I said, you know, we have data through a network of electronic health records of over 20,000 people, and I've seen a bunch of comorbidities. In fact, I've seen 5,000 diseases in these kids other than autism. But what I'd like you, Phenome, to do is to see if you can actually subset in an information theoretic way these patients into distinct subgroups based on their characteristics. And what she did was very, very beautifully simple. So I told you there was 5,000 comorbidities, and because of the data we had for about 20,000 kids, she was able to get about 15 years of data on each of these kids. And each 6-month block, she would turn into a 5,000 bit vector, where there would be a 1 if you had that disease and a 0 if you didn't. So obviously, when you clustered them together, patients who had similar diseases at approximately the same time would be closer to one another than those who had different diseases at different times. It's clear so far? And so what she did is she clustered the entire group, and as a result, by the way, just one last bit of context, part of what was driving me that was not only Ari Ne'eman's point of view that he had autism and therefore everybody with autism should be treated the way he wanted to be treated, but that a lot of parents were coming to me, and I'm not trained as a neuroscientist, but they knew I was doing autism research, and saying, my kid has a lot of bowel problems, they're bleeding from the anus. I think this is part of autism, but my pediatrician doesn't say so. And when I went to talk to pediatric developmental specialists, they said, brain bad, tummy hurt, verbatim, and these by top specialists. So I said, let's look at it. And when Phenome did the clustering, what we found across this network of hospitals is there was one subgroup that, although there is seizures in autism, actually about 20%, there was a subgroup that had 90% seizures. There was another subgroup that had a lot of autoimmune and infectious disease, so immune dysregulation, lung infections, ear infections, sinus infections, as well as type 1 diabetes and inflammatory bowel disease. And a third subgroup had psychiatric disease, like ADHD, anxiety, depression, and very significant but a much lower rate, schizophrenia. And my point is this: in most of our autism studies, whether we're doing exome studies, whole genome studies, or common variant studies, we treat it as autism versus not autism. It's a categorical thing. But in fact, if it's 3 different diseases, and I'm telling you that's more than that, we're completely, as a result, destroying the signal and therefore the power of our study. Whereas we could really increase the power by finding the distinct subgroups, but by insisting on this categorical nature of the disease, by DSM-5 criteria, for example, we make all of us blind to this. But it makes as much sense as if I said we're going to do a heart failure exome study. We're going to put on the one side heart failure due to both valvular disease and viral infections versus not heart failure. It makes no sense. They're different pathophysiologies. They involve the same organ. They have the same symptoms, but they're not the same disease. And so we have to be aware of that. Next, here's another group of individuals with arguably a disease or not. These are very short people who typically have problems either with growth hormone or growth hormone signaling receptors or further downstream. And I did tell you I was trained as a pediatric endocrinologist, so I know a lot about this population. And one of our big victories before, this is my academic ancestors, one of the big victories was to take, this bizarre thing, 60,000 cadavers, take the pituitary glands where growth hormone is made, put them in the blender, and extract enough growth hormone to treat several thousand kids across the world with severe growth hormone deficiency, bringing them from the 4-foot height, where you're really incapacitated and socially disadvantaged, to the 5-foot range. Problem was, in the 60,000 individuals that we blenderized their pituitaries, there was a few who had Jakob-Creutzfeldt disease, who had a slow virus, and we basically killed quite a few kids. And so I didn't see it. This was not my experience, but it was the experience of my mentors. And so as a result, when recombinant growth hormone came to the market, even though there was no possible way that human Jakob-Creutzfeldt virus would come into it, they ended up being very conservative in the dosing, giving about a third of the dosage of growth hormone. So what happened then, let's see, do I have, yeah, so what happened then is I wrote, as a very young fellow in training, a small abstract where I compared the growth hormone experience in our clinic, where we're giving a third of the dose of growth hormone. By the way, growth hormone costs $10,000 to $30,000 a year. And so we were given, because of the experience with Jakob-Creutzfeldt, of my mentors, a third of the dose. And I compared it to the National Genentech experience. No difference. And I put it up abstract, and I got a call from the chief medical scientist of Genentech saying, Dr. Kohane, do you realize I sit on all the journals that you could ever possibly want to publish in? Why did you not share this abstract with us? And why was that important? Because the fact that I was saying that you could get just as good outcomes with low dose would threaten their bottom line. This is going to happen with all of you if you come up with any biomarkers that reduce usage of a drug for which there's a current fixed price. There are big stakes in this disease, and they have been brilliant at disease definition. What is the definition? I don't know if I have a slide, so I'll just tell you. The disease definition of growth hormone deficiency, or giving growth hormone, the disease that you give growth hormone for is either growth hormone deficiency or -2 standard deviation height and growing slow. What's the problem with that definition? It means no matter how tall the population gets, you'll always have your customer base, because there's always going to be the bottom tail, no matter how tall. So it's a genius kind of definition of disease. It's always the bottom tail. And so I just want us to be aware of this. These disease definitions turn out into billions of dollars and huge pressures for you to actually define them or not. And in the context of what we know is going on, where my colleague Joel Hirschhorn, himself, by the way, a pediatric endocrinologist, when he ran the giant study, they found that there's probably around 700 common variants that inform height. And so each individual variant, as usual for common variants, has a very small effect on height. But this is a huge number of opportunities to say, oh, you have the minor allele, you're shorter than you would be otherwise, let's treat you with growth hormone. And so this is what I told you about. And just to show you that I'm not imagining this, this is a story which I'll just quickly summarize to you. Well, actually, why don't I say it to you? This is another endocrinologist, not me. About once a month, an ambitious parent with cash to burn asks de Rosier, a pediatric endocrinologist in Florida. So just last week, the father of a young baseball player, a 14-year-old who was already 5'6" expected de Rosier to prescribe recombinant growth hormone to add height to his budding athlete. He wanted to make his kid big and thinks he's going to walk out with shots. He was willing to pay more than $45,000 a year. Now, I actually don't fault the parent. Maybe this is the right thing. Maybe this is the right thing for this kid. But the point is the disease definitions that we are going to create are going to influence this kind of behavior again and again. Here's a disease that is 1 in 500. And you know about it even if you don't know its name, because it caused famous athletes to drop dead on the basketball court. Like, well, you know many of the names. So it's hypertrophic cardiomyopathy. Only a handful of genes are involved. It's autosomal dominant. And therefore, if you come into a clinic and you have an enlarged ventricle, or you had an irregular rhythm, or you pass out on the basketball court, and you have one of these variants, you'll get the whole 9 yards treatment, including an implantable defibrillator, and because it's autosomal dominant, all your family gets evaluated. So again, this postdoc of mine, who by the way is another PhD, Harvard undergrad physics, PhD in computer science at MIT, Rajman Rai, and he looked at the ESP database from the National Heart Lung Institute. Nowadays, a relatively small, about 10% the size of exact database from the National Heart, Lung, Blood Institute. And based on the 1 in 500, you expect that much red to be present in the population. But then when Raj looked at it, there was that much red. Way too much red for a 1 in 500 disease. So what's going on? So he looked much more carefully at it, at this disease, and he found, for those variants, in African Americans shown in red, 20%, 15%, 5% prevalence of this order of variants that are ostensibly textbook autosomal dominant hypertrophic cardiomyopathy. And I hope that, unlike every other audience, medical audience I would talk to, you'd appreciate that that's not consistent with a 1 in 500 disease. And I hope also that there's enough population genetics in this room that you'll appreciate that Africans who came from Africa as slaves in the last 500 years are bigger representations of Mother Africa with all the heterozygosity that's present there compared to Asians and Caucasians who came out either 60,000 or 2 million years ago, but nonetheless represented a bald neck and therefore a tiny sample of the overall variance. So if you look at an average Asian or Caucasian, they have much less heterozygosity than Africans or African Americans or African Europeans. And so the point is this. Nobody in population genetics would believe this, but it is true that what happened, and we verified this, is they got the study design of these very high-profile papers half right. So they got ethnically matched controls, white. And so they got white, because they knew they were going to get a bunch of white cases. The problem is, for a 1 in 500 disease, it actually takes time to recruit all those cases, so they didn't look quite as specifically as they should have into the ancestry of them. And so a few of them, turns out, for example, in the Paris study, were from North Africa. And so then, by virtue of being on the case side of the study, not the control, the case side, you may look like you're a white European, but you have some African ancestry, and you have variants that are absent from the white population. And you're into the study because you had a larger heart, a thicker ventricle, maybe you passed out, but now you have this variant. A study says, not seen anywhere else, rare causal variant in that gene. Goes into the books, and that's it. That's what happens. And so people are being diagnosed and have things done to them and to their families because of this much misunderstanding. And this is one of our best clinics in the world. And these are all shown patients misdiagnosed in exactly this way. This is live ammo. It's worse than that. It gets back to our breast cancer example. There is a study now, I just looked it up, in clinicaltrials.gov for hypertrophic cardiomyopathy, for a drug, valsartan. And if you scroll down, you'll find here that there is a preclinical group. In other words, no clinical manifestations, normal size heart, and everything's normal, except you're positive for the genotype. All you have to do is be positive for a genotype, and you're in the study. And you could be as young as 10. So you could put a 10-year-old whose only evidence is a genotype, which could be wrong, and that's enough to put them for years on a drug. And it'll be a success because they didn't have the disease. Another great win for medicine. This is why this fake disease thing is absolutely critical. Now, is prediction the acid test of diagnosis? I was visited by a very dapper, efficient-looking CEO of a data science company from Silicon Valley, who used to be, still is, a former MIT grad, worked with Google a lot, and now was in the Boston area doing business. And he came to my office to see how things were going on, and I said, you're a smart data scientist, CEO of your extremely well-funded Silicon Valley company. Explain this to me. See here, if you're in my age group, 50 to 69, and you're white and male, and a blood draw showed that your white blood count between 12 a.m. and 8 a.m. is low, you have a low white blood count, your chance of dying in the next 3 years is greater than 50%. I said, how is it that if you draw that blood and you find that low at 8 a.m. to 4 p.m., you only have less than 3% chance of dying? What is that? To give this guy credit, he thought about it hard, and he said, circadian rhythm, I'm here to tell you, there's no way circadian rhythm can do that. I said, no. The explanation is that when a doctor draws blood from you at 3 o'clock in the morning, it's not because they're trying to annoy you, it's because you're trying to die. You're very, very sick. And it turns out there's a whole other layer of decision-making on top of the data. The data is part of two different physiologies. The physiology on the one side of the patient and the physiology of the healthcare system. I don't have time to show you about time of the year, which clinic and so on. There's a lot of information about the way medicine is done, the physiology of the healthcare system, or as I like to call it, healthcare system dynamics. That if you're a typical Google data scientist, you see this as noise. Problem with that, A, it's not unbiased noise, it's biased noise, just as we found out in the elections on the polls. Second, if you understand it, you can actually improve your predictions. And so in this unpublished data that I'm going to show you here, on the x-axis is essentially survival odds. On the y-axis is the contribution of this, each data type to understanding the survival. And you can see here, lab tests where regardless of the value, just the fact that the value was obtained is predictive for mortality. And you can say, Zach, what's that important? Well, it's going to improve your prediction. We're in the dream challenge here. If I want to improve prediction, when the data was obtained, under what condition, and with what intentionality is going to be hugely important as to the diagnosis. To ignore it is to ignore the real world. And of course, if you combine the two, the actual value and the health system dynamics, you improve the prediction performance. That, my friends, is what real disease prediction looks like. And I just want to tell you that I just heard about Docker and Amazon, and so we've been trying to do this for real. There's a program called, how am I doing on time? 5 minutes left?
No, more.
Oh, excellent, thank you. So I'll slow down a little bit. You know, by the way, I'm a little bit overly manic because I really did not sleep last night, and so I'm trying to give myself energy to be coherent for the last 10 minutes.
That's why I look like a zombie. So.
What?
That's why I look like a zombie.
Yeah, exactly. Oh, same reason. There we go. Yeah. Yeah, so it's easier to be up here where at least I'm talking and you just have to listen. Got it. So there was a very interesting program at NIH called, and still exists, Undiagnosed Disease Program, where they had this amazing thing. Patients who had not been diagnosed for years and were doing really poorly, suffering, some dying, and for years had not been diagnosed. And by the way, this is very expensive, costs millions of dollars a test. And they were seen at this program where they obtained, at the time, this was starting 8 years ago, something that was at the time cutting edge, an exome, plus referring them to the right doctor in the Bethesda area to evaluate them. And they achieved 60% meaningful diagnosis rate, which is, I know that sounds not huge, but that's huge. 60% meaningful diagnosis where people have been refractory to diagnosis is actually an unbelievably good outcome. And what happened as a result is patients started coming to them, but they were out of bandwidth. So an amazing thing happened. Republicans and Democrat congresspeople started complaining to the NIH, how come you're not seeing my constituent? They said, we don't have the bandwidth. So there was bipartisan agreement to blow this up to a $250 million program, national program involving all those academic health centers. And I proposed to be the coordinating center for this. And what I proposed specifically in the plan was to say, we're gonna take all the data, genomic and clinical, and we're gonna shove it into the Amazon cloud, make it HIPAA compliant. By the way, also FISMA compliant. I had never heard of FISMA. That's a federal standard of data security because we had NIH patients, so you had to also be there. And it turns out we could do that. I said there was no intellectual property stickiness. If the patient was referred from one of those centers to another center, no friction whatsoever, and the data goes with them. All the data is available to every researcher in the network, and we made sure that at the national level, we would put them in touch with the right investigator. And it took us about a year and a half to put up the infrastructure, and this is out of date now, but we've already received about 1,000 applications, and there's now several dozen new genetic diseases that we've discovered as a result. And in some ways, it's a model of what I'd like to see. So what about the increasing overlaps across diagnoses? I'm sure most of you are aware that there's increased awareness that for a variety of conditions, there's shared alleles across multiple disease types. And let me just share you quickly a study that I did with Bonnie Berger, and I shared postdoc Sumayan Nazim, who this paper is going to be published shortly in Genome Biology. And so I asked her, back to this autism, what genes are actually shared? What genes have variants or expression even shared across the comorbidities of autism? Is there a shared pathway? And it turns out there was a lot of shared pathways across these different diseases, but the top one was this one, innate immunity, toll-like receptor signaling. And which is pretty interesting that there's a common theme across all these diseases of this dysregulation of innate immunity. And so how do we accurately, how do we understand the contribution of these genes? We could actually use those genes to actually classify each of those diseases. So use that pathway across each one of those comorbidities. And it's not clinical grade AUCs, but there's real signal that I assure you is not random across each one of these comorbidities. Similarly, there was a study done by this psychiatric consortium on schizophrenia, bipolar disorder, major depression, ADHD, and autism. And there were a number of variants that were shared. This is, I think, was a common variant study. Yeah. And in this case, the common variants that were shared were in the calcium signaling pathway. So here's the question I have to ask for you. Now that I told you that, what's the disease? If you have schizophrenia, is it only the true blue part? Is it the true blue part, or is it a set of variants that go across all components of blue? There's no right answer here, but it's an answer that is going to have to be answered. It's a question that's going to have to be answered pretty soon, because if we see these overlaps and they have some prognostic values, yet there is overlaps, how do we balance shared symptoms, distinctive symptoms, shared genetic variants, distinctive variants? And so, in closing, I want to ask you, what are going to be the clinical, can we start thinking about the clinical pragmatics, things that actually matter to patients, versus state-oriented classic definitions? Because right now, most of the disease definitions are state descriptions of the patient. Maybe we have to have a more instrumental kind of definition. So instead of schizophrenia, the definition I showed you, instead of growth hormone deficiency, the height velocity definition, or autism, describing your ability to interact with people, repetitive behaviors, and so on. Instead of that kind of definition, perhaps we should describe it as an equivalence relation, where perhaps one equivalence relation might be gets less hallucinations with drug X. Now that's not a complete definition of everybody that we have put it in that blue box, in blue circle, but it's actually something that is pretty concrete, and that if we know if someone fits in that, we know what it would mean to treat them in the precision medicine context. Grows to within -2 standard deviations in response to growth hormone. Again, it doesn't say what the disease is, it just says what is the expected useful clinical response for that patient. Or scores -3 standard deviations on emotional intelligence. Those are the kind of definitions that I believe become much more useful, are much more reproducible, and will maintain themselves in this era of multimodal descriptions. And certainly we can combine these categorical descriptions in, for instance, Boolean fashion. For example, this might be a kid with Rett syndrome, scores -3 standard deviations on EQ, loss of function mutations in the MECP2 pathway genes, and complains of abdominal pain. You could create that equivalence relation. But I would still argue that there's a better way that you already know, which is to really do a full embrace of multivariate, multimodal, nonlinear population models. I mean, this is what you're doing all the time in your competitions. But I think there's a significant challenge there. in the clinical realm at least, because of the black box, gray box nature of the algorithms and the lack of a intuitive, and you're quite aware of this, lack of an intuitive summary that a patient or a doctor can hang their hat on. And so this will either be an educational challenge or an implementation challenge or both. And my pitch to you is that you actually represent the right team to actually think about this. How does one actually represent that kind of multivariate, multimodal diagnostic? There are very few groups such as this one who are capable of actually answering that question in a principled way. And that's the advertisement. Consider joining us at the Harvard Medical School Department of Biomedical Informatics. Now, here's the other ad I was telling you about. So when Jeff Drazen wrote an unfortunate editorial maybe a year and a half ago now, where he was actually quoting someone else, describing us as research parasites. Big storm happened, and I approached him and I said, you know, I think you've created an opportunity to have an interesting discussion. Let's have a discussion, let's invite a lot of people. And he was game for that. But off the record, don't tweet this, the New England Journal of Medicine board thought this would go away. And then Marshall McNutt, who was, I think, then the editor of Science, wrote an article about I am a research parasite, and it continued going on. And so they were convinced we should actually do something about this. So Jeff approached me again, and we have a great opportunity. So the capstone of this is a conference in April of 2017, where we're going to get together. They're calling us the data analysts, but I wear the badge pridefully. The research parasites, the trialists, and the patients will get together to talk about what is a healthful ecosystem to actually be able to look at clinical trials data. Now, we've been talking about a lot of data types, but clinical trials data is pretty important because it tells us what's the right way to treat patients based on, typically, an RCT study design. And so, to get into this conference, you have to do the following. Go to this website, and they made the data available on a interesting hypertension study that was published a year ago, but the data is not available, was not going to be made available for a while, called the SPRINT trial, where we're looking at aggressive lowering of blood pressure beyond the current criteria to see if it would actually help anybody. And you'll just have to answer a few questions about the data, and if you do, then you can use that data in combination with whatever other data you want to answer interesting questions. They don't have to be the standard clinical questions, any interesting questions. There'll be a judge. We've got an interesting group of people judging, including the very critical and now crestfallen, because of the election, Mike Eisen. And so let me just encourage you to apply to the challenge. So with that, I just want to close by thanking my several collaborators in the particular studies you saw. And I recognize that I really flew through many of these aspects of what I call fake diagnoses and dangerous genotypes and phenotypes. But if any of you have any comments, including critical ones, I'll be glad to entertain them. So thank you. Yeah, Jonathan, the zombie.
I actually applied to be an extra in a zombie film and they turned me down, so
Seriously?
the diagnosis was wrong. So.
There we go, another false positive.
All the information about the confounding of the time of day, the test was taken, etc. It's all brilliantly insightful and great, but it's very rare that you get that kind of information with your big genomic data set or what have you. And to collect all of the right information, you've obviously got to, you often got to get a little bit from this hospital record, a little bit from that claims record, and involves combining data that we don't currently know how to do, and there's a lot of restrictions to how you can do that and so on. So have you got any thoughts on how we bring the right information together?
I do. So I can tell you early on in TCGA, they were really focused on all these omics measurements. And when I started asking them about the clinical characteristics of the patients, they barely knew anything. Now, to be fair, they subsequently improved that a lot. But there was actually no reason, I mean, we spent tens of millions of dollars on TCGA. It would have taken just a few $100s to a medical student to actually go and create a nice data cube about each patient so that a lot of the questions that we had would be answered. And so I would argue for things, well, first of all, if the open data initiative that I was describing for the hypertension trial comes to pass, because really what we're trying to do is to publish the primary data for the trials. If that comes to pass, that in some sense solves the problem, at least for the trials. But more importantly, I think that don't be afraid of the medical records. If you're afraid of it, you know, I actually, my PhD students, I send them out to the clinic and so to demystify whatever these doctors do so that they understand it. And for these DREAM trials, I'd get a whole bunch of data that may actually seem irrelevant, but just be as comprehensive, systematic, because someone's going to pick up a signal like those kind of ones that I showed you that no one actually thought of. And they may, you know, you'll see an outlier, and my gosh, the RNA quality seemed to be good, and the clinical, but there's something about that patient that didn't make it through, like they were on another treatment before that that's changed some epigenetic state that wasn't captured. And just having a good, deep, so I think my very local and modest proposal is for future DREAM challenges, trying to be very comprehensive on the clinical record, whether or not it's relevant to any of the metrics that we think are important in the prediction task, might be useful in debugging some of the interpretation.
Thank you for that insightful talk, and I totally agree that we should be more quantitative in the equivalence relationships and try to be able to capture the uncertainty in the clinical data. I was just wondering for interpretation, because me as a bioinformatician, and most bioinformaticians want to make an impact on patient care, right? I was just wondering, how do you translate kind of those equivalence relationships to the patient? Because it doesn't seem kind of intuitive. I mean, for me, even as a patient, right, whether a drug improves, you know, EQ by 2 standard deviations,
right.
What does that mean in terms of my health?
Well, let's again, in my sleep deprived state, I'm not exactly sure what my answer is going to be to you, so I'm going to role play it in real time with you. So let's say, God forbid, you have a bad cancer. And as usual, there's a lot of heterogeneity in the tumor, and there's different driver mutations, but across all of them, there's a pathway that looks like it might be responsible, some RAS pathway that is treatable. Now, you're not sure which of the 20 types of breast cancer this is, but you know it's treatable by that. When the patient comes to you, and they'll actually think that you're a real smart honcho if you said, you have breast cancer, I don't know which of the kinds it is, but whichever kind it is, it will respond to this, it seems to will respond best to this treatment, they'll think you're a god. Because in fact, you'll be better than any doctor. Because in that instance, it matters less what the exact diagnosis is than saying this is the right thing to treat what ails you. Now, things are a little bit different when you have no treatment. And I can tell you a bizarre thing that I never used to understand, now because of the Undiagnosed Disease Network, I understand better, which is if you have no treatment and you're suffering, so a lot of patients get a lot of comfort from having a diagnosis which actually has a causal mechanism, even though there's no treatment. But that's the unusual case. I'm just telling you, for most cases, given the heterogeneity of diseases, I mean, there's cancers are heterogeneous, but all the things that we know have a big, common diseases have a big, as you know, environmental component, because heritability is typically 50% on average for the common diseases. So they're complex, they're not all the same thing, and so giving them an operational definition of what their disease is in terms of a treatment plan, you'd go away saying, this doctor's really smart. I don't know if that's compelling to you, but that's the best I can do on short notice.
Great, thanks.
I'll just echo the comments. Thanks again for the talk. Where do you think the leadership will come, or where have you seen it for the subtyping of patient groups to better define? Is it patient advocacy groups and parents of these autistic kids, clinicians, experts?
So definitely, in part, is patient advocacy groups, and I don't want, because I can sense the hook coming to drag me off the stage, so I just want to refer everybody to a computer scientist by the name of Matthew Might, who, if you read up the New Yorker, one of a kind, it'll tell you how he basically drove a lot of his kids' diagnosis and creating a cohort about a genetic disease that was the first ever diagnosed. So patient diagnostics is one. But I think the second is the $100,000, $200,000 a year treatment. For a rare disease, I do not begrudge any patient that. I can assure you, if I have a family member who can benefit from a $200,000, I will figure out how to get that medication. But the problem is, if our pie of cancer looks like this, we can probably afford to do $100,000 a year for a sliver of the ones that we find some driver mutation. But if we are fully successful as a group, and those little pilots end up being the whole thing, that is bigger than the US GDP. Therefore, if we can actually provide those kind of operational definitions at that key point where we're running out of money, which will happen soon, and identify the patients who we can pay, that it makes sense for society to pay for. In the end, people can find other sources of money, but as a society, the ones that we're willing to pay for collectively, so I'm talking about the insurance companies or the government. We will need those case definitions to make that argument. Again, right now, when we're still a tiny fraction of our cases are these few $100,000 diseases, but it's rapidly expanding, and in the end, we're going to run out of money, the big money, and so we will have to have those focused case definitions. I think that's going to be the real driver. So initially, I think good proof of concept cases coming from patient advocates, but ultimately, it's the way medicine is going to be, and we're going to be. So either it's going to be a patient-friendly decision theoretic framework or a patient-unfriendly, and I hope we're going to be part of the solution here so we can make it more patient-friendly.
Last question. Thank you, Zach. It was a very provocative and interesting talk. I think that this issue of classifications, right, are pervasive in science since day one. You know, we used to think of four elements until we finally learned something else about, you know, how the world is structured and created. Not created, but, you know conformed.
Yep.
Let me read you something that I love about classifications.
All right.
Because I think this will continue to be so. I mean, when we look about genes, you know,
Yep.
we have this gene ontology, which is,
No
matter how you look at it, it's a little bit ridiculous, right? But we need to start somewhere. And I think that even in the chicken and egg problem of defining multimodal markers for disease, eventually we will have to make decisions. But this is funny, and I want to...
And I'll give a response to you, but I want to hear the funny one thing.
So this is by an Argentinian writer called Jorge Luis Borges.
Of course.
Who wrote...
A very funny humorist who I recommend to all of you young people who have never read him.
I don't know whether you know this about his classification of animals. He says, talking about the problem of classification, says, these ambiguities, redundancies, and deficiencies remind us of those which Dr. Franz Kuhn, which is a fake person, attributes to a certain Chinese encyclopedia entitled Celestial Empire of Benevolent Knowledge. In its remote pages, it is written that the animals are divided into belonging to the emperor, embalmed, tame, sucking pigs, sirens, fabulous, stray dogs, included in the present classification, frenzied, innumerable, drawn with a very fine camel hairbrush, etc., having just broken the water pitcher, and that from a long way off look like flies. So I think that this is
that is beautiful. And so what I'm saying to us as scientists, and we are scientists, is because we in this new era where we do have that multimodal opportunity, if we see lack of coherence or lack of perfect correlation across these modalities, so that things seem to be splitting apart, don't think, oh, there's something wrong with my algorithm necessarily. Ask yourself, is the fundamental nature of whatever you're trying to represent actually not unitary, and it's broken apart? The tension between the splitters and the lumpers is going to be eternal, but I think that as long as we are aware that there is a tension and that where you sit on that spectrum will depend on what you're trying to do, I think we'll be much, much better, and we'll avoid making some of these bizarrely reductionist errors that I described to you that very smart people did just because at some point they just put their heads down, they stopped asking themselves, why is the data going this way and that way? So all I'm saying is you have the tools to actually be nimble ontologists and epistemologists. And with that, I thank you, and congratulations on a wonderful meeting.